Hello everyone, and welcome to the first module of Chapter 7. So this chapter is on memory. It should be a pretty interesting one for you. I think you'll find it long but hopefully enjoyable in terms of some of the things you'll learn that are really relevant to daily life. And hopefully the information you take away from this chapter will actually help you with your own study habits and memorization techniques and things like that as well. So I am going to apologize in advance. I'm back in Manitoba now, and I do have two small and very vocal dogs. So if you hear any random barking during the lecture, that's why. I am also going to stick to the non-video lectures only because the file sizes were gigantic for the video lectures. Unless anyone has any major complaints and really wants video lectures, I can try to do some, but for now I'm going to try to stick to the audio only. So we'll get started with this module, and I will say module 1 in this chapter is the longest of the three. Just over half of the slides I have for this chapter are in this module, so this is definitely going to be a long lecture. If it does run past 50 minutes, which I'm really hoping it doesn't, then we can always kind of pick up where you left off on Friday when you watch the class for Friday, because definitely the module 2 and 3 will not take the full 50 minutes. So if this one does take a little bit longer, then feel free to watch, half of it or 75% of it for tomorrow's class and then the rest for Friday's class. I don't want you to have to watch more than 50 minutes per class, but it definitely will even out over the course of the chapter. So, chapter 7 is memory. Here are these dogs I was just talking about, the really loud ones. Even when I'm gaming, Turbo likes to relax on my lap and get in the way. So when we're talking about memory, there are a lot of different things we can consider. Do you think that people who provide eyewitness testimony in court, that their accounts are always reliable? Another question we might ask is, when should we trust our memories and when should we be skeptical of them? So a lot of people assume that they remember what they remember, but in reality it turns out a lot of the memories that we have are false or altered in some way. We know it is possible to forget, but is it possible to remember things that did not occur? Are memory malfunctions rare, or do they occur commonly? And then finally, if our memory may not be reliable, how can we hope to know the story of our lives or understand the past? So these are just some of the questions we're going to kind of touch on as we go through this chapter. Unfortunately, the older textbook I liked a lot better. It started with the false memory information. This one doesn't really bring it up until the last module, but in this module we'll talk a bit about how memory is organized and the different types of memory that have been theorized. So let's get started. First off, I want to start with an example. This is a lot more dramatic if we're actually in a classroom, so unfortunately you won't really be able to see people raise their hands around you, but I want to try it out, and please don't cheat. Listen to the instructions carefully, and I want you to kind of raise your hand or maybe even make a check mark on your book, on your notebook, as to whether or not you remember hearing these words. So basically I'm going to read you a list of words, and then I'm going to ask you, I don't want you to write them down. I don't want you to try to memorize them. I'm going to try to read them pretty fast, but hopefully they'll be kind of kept in your short-term memory for a little while. And then I'm going to ask you whether or not you recall hearing certain words. So I'm going to start the list now. Butter, jam, crust, food, milk, slice, eat, flour, wine, sandwich, jelly, loaf, rye, dough, and toast. So that's our word list, and now I'm going to ask you if you remember hearing certain words from the list. So just make a little check mark on your notebook if you remember hearing these words. Do you recall the word sandwich? Do you recall the word crust? Do you recall the word slice? Do you recall the word dough? Do you recall the word bread? Now, if you said yes to that last one, to bread, that actually wasn't a word on the list. And I know a lot of you, if you did kind of remember or think you remember hearing bread, you can go back and check if you want. You can listen to the whole list over again, replay that little section. I did not say the word bread. The reason you might be thinking you heard the word bread is because of this paradigm called the DRM paradigm. So basically what happens is the participants are given a list of highly related words. So I gave you a lot of words that are all related to each other: the butter, the jam, the crust, the food, the milk. they all share some kind of semantic property, so a similarity in meaning. But there's one word, which we call the criticaler, that I leave out. That's related to all of the other words on the list, but I leave it out. And so basically what I'm hoping is that by giving you all those words that are super related to each other and super similar in meaning, that you will kind of create a false memory of having heard that criticaler, even though it wasn't actually stated. So that's just one kind of really interesting and kind of silly in a way, but it is an example of a procedure that is used in memory research. And it's just one way that we can illustrate that false memories really aren't that hard to create. So maybe your memory is not as great as you might have thought it was. And I will admit, after reading these chapters and teaching about them for so many years, I now question my own memories of things. So if you're kind of questioning yourself at this point, you're not alone. So now we'll get started with the real kind of bread and butter, to call back to that list of the chapter. So we're going to talk about the memory systems, so how we conceptualize memory and its different components. So in the 1960s, two researchers named Richard Atkinson and Richard Schifrin constructed a memory model that included 3 memory stores. So these were known as the sensory memory, which basically retains incoming sensory information for a matter of seconds. You have your short-term memory, which holds a limited amount of information briefly. And then you have your long-term memory, which can hold information for longer periods of time. So what we mean by memory stores is that stores are kind of like, you can think of them almost like buckets that retain information in memory without using it for any specific purpose, while things called control processes shift information from one of these stores to the other. So information can pass from your sensory memory into short-term, and it can pass from short-term into long-term, but it can also be brought back from long-term into your short-term, so kind of back for use at present. So despite the fact that a lot of people like to refer to memory as one single faculty, something, I have a bad memory or my memory is faulty, the term actually covers a complex collection of processes and abilities. So information enters the sensory memory through our senses. So the light waves we take into our eyes, the sound waves we take into our ears, that's how the information initially enters our senses. And the control process that we call attention, which I'm sure is a word you've all heard of before, selects which information will be passed on to our short-term memory. So basically what happens in your sensory memory is you get all of this incoming sensory information, but we can't possibly pay attention to all of it. We can't possibly hear every sound and see everything in our environment. So attention decides what is most relevant for us to kind of focus on and pass into our short-term memory. Then we narrow the information received in short-term memory even further through encoding, which is basically the process by which we take information from our short-term and kind of store it in our long-term system. And then we can use another process called retrieval to bring the information from the long-term memory back into short-term. So if you need to use information on how to complete a math problem, and you learned how to do that in, say, grade 2, then you're going to take that information from your long-term memory and bring it back into the present for use to complete that math problem. So this is just a little diagram of what the Atkinson-Schifrin model looks like. So you can see we have our sensory memory, and information when it's taking it into sensory memory, it's either lost, or if you pay attention to it, it goes to short-term. We can keep information in our short-term memory using a process called rehearsal, where we kind of repeat the information over and over. And at that point, it can either be lost, or we can encode it in some way. We can do work on it to get it to encode and be stored into our long-term memory. And unfortunately, even our long-term memory at times can be subject to loss of material, but we can also retrieve information from long-term and bring it back into short-term for present use as well. So there's a bunch of different kind of directions that information can be flowing within this model. So now we'll talk a bit more specifically about those 3 storage components. So our sensory memory is a memory store that accurately holds perceptual information for a very brief amount of time. So basically all of the sight information and the sound information and all the other sensory information that you take in is held for a very brief period of time, and your short-term memory, your attentional process then has to determine whether or not it's important enough to kind of take into short-term memory, or that you can kind of just let it slip and it'll be lost. So 2 types of sensory memory include your iconic memory, which is your memory for visual information, and this lasts for only about a half to 1 second. and your echoic memory, which is your memory for auditory or for sound related information. So that one lasts a little bit longer in the sensory store. It can last for about 5 to 10 seconds, but still, if you don't pay attention to it after that 5 to 10 second period, it will be lost as well. This memory acts as a holding bin, which retains all the information that we receive in a highly accurate form. So it holds a ton of information at once, but if it does not quickly move to short term, it will vanish forever. So although sensory memories disappear faster than they can be reported, Sperling, who was another researcher, argued that the storage capacity of sensory memory was actually very large. So it's hard to assess sensory memory because by the time you ask somebody to recall what they saw or recall what they heard, that memory is already fading kind of from their memory, just because if they haven't paid attention to it, they wouldn't have processed it. But Sperling devised a really unique way to kind of try to measure whether or not that sensory information was actually being taken in. So basically what he did is he showed them a grid of letters that he flashed on the screen for a split second, and then he asked them to attempt to recall as many of the letters as possible. So when he's flashing them, as we know, our iconic memory can only store information for 0.5 to a second, right? So in the time it took for them to start reporting what they had seen, that memory was already gone, and they were only able to report maybe 4 letters, so approximately 4 items, which is kind of what would have consisted of a single roll in this case. But Sperling figured that you could actually take in all that information, you just weren't able to recall it because it had disappeared so quickly. So what he did then is he did a partial report task where instead of asking them to just recall whatever they could, he showed them the flash, then he played either a high, medium, or low tone, like a little sound, which corresponded to the row that he wanted them to report. And he found that people were actually accurately able to report any row that they were asked about. So it wasn't that they didn't take in all, say, 12 letters at once. It was that in the first condition, they were only able to report so many before it disappeared from memory. But in reality, their visual system was actually taking in all 12 digits. It just didn't really have the capacity to store any more for them, or to kind of report any more for them before that storage kind of failed and that memory slipped away. So it was a really interesting experiment that showed us just how much information can be taken into sensory memory at any time. So basically, a few other facts about sensory memory. During the transfer from sensory memory to short term, we do identify stimuli based on information held in our long-term memory. So because we have experience with a lot of different stimuli, and all of that information is then stored in our long-term memory, we can use that to help us identify what we've been taking in from our environment and decide whether or not to pay attention to it. So attention allows us to move a small amount of information from our sensory memory into short-term memory, the information within the spotlight of attention. So basically, like we said with that little picture I just showed you, depending on what they were kind of focusing on and asked to report, they were able to transfer that small amount from the sensory memory into their short-term memory and report it back to the researcher. Unfortunately, there is a limit to how much information can be transferred at once. And if you think of that, it is kind of adaptive in a way, because if you were to have to take in every single sight and sound you ever heard and saw and basically pay attention to all of them, you would go into sensory overload. So it is kind of adaptive that you can't take in all of this information at once. So there's a phenomenon known as change blindness, which illustrates the relationship between sensory memory and attention. So I'll show you a little figure here that will kind of explain a bit about what that is. So basically what happens in a procedure like this is that they show you a picture, they flash it, then they flash a blank slide, and then they flash another picture. And there is a subtle difference between the two pictures. So basically they just keep flashing back and forth until you're able to respond and say what you think the difference is. And basically what happens is, because they're being flashed so quickly, whatever you are focusing on in the moment, whatever it is that you're kind of honed in on in your visual field, is what you're going to end up seeing. So if you're not honed in, if you're not focusing on the part of the picture where the actual difference is, it makes it very difficult for you to identify the difference between the two pictures. However, if you were paying attention to the area that differed, which in this case is the end of the branch there, you can see in A, there is kind of an extended branch, and in B, that piece of the branch is missing. So if you were focusing on that particular area of the picture, you would be able to report the difference. But because they're being flashed so quickly, say if you were trying to scan the birds and look at if the difference was in the birds, you'd probably be likely to miss that change because it wasn't in that focus area of attention. So that's what they mean by change blindness. So next we'll talk a bit about our short-term memory store. So short-term is a memory store with a limited capacity and duration. So with the sensory memory, we said it has a very high capacity but short duration. Short-term memory has limited capacity and limited duration. So you can only store a little bit, and it can only be stored for approximately 30 seconds. So a little bit longer than your sensory information, but not much. So there was a researcher named George Miller, and he estimated that the capacity of human short-term memory was about the magical number 7 plus or minus 2 digits. So basically that we can store about 7 kind of chunks or pieces of information in our mind, plus or minus 2 pieces, depending on individual differences. So some might only be able to store 5, others might be able to store up to 9, but typically we wouldn't see many people being able to store much more than that or much less than that. However, when he says pieces of information, it doesn't necessarily have to be like a single digit or a single letter. We can use something called chunking to help us organize the information into larger, more meaningful units. So if we are given a bunch of letters, so for example, if you look at this first list of letters here, O, B, T, N, C, H, C, you can see that the letters are kind of meaningless, and if I asked you to remember that list of letters, it would probably be very difficult for you to repeat all those letters back to me, right? Because they're all random letters, and there are far more than 5 to 9 of them. However, if I take those letters and organize them into a meaningful pattern, like in the second example here, you can see that we have CBC, HBO, CTV, TSN, CNN. So by chunking those letters into meaningful units, in this case into the acronyms for popular television stations, I bet that you will be able to recall this whole list of 15 digits then. Even though it's more than 7 to 9 digits, because we've chunked it into 5 chunks based on those TV channel abbreviations, you'd probably be more likely to remember all 15, because instead of remembering 15 individual bits of information, you're remembering 5 chunks. There's also an analogy of short-term memory being like a leaky bucket. So this is said because our short-term retention can be frustratingly brief, especially because we can only hold so many digits of information or so many chunks of information and only for a very short period of time. But if you think of it logically, if the bucket didn't leak, so if we didn't slowly lose all that information over time, unless we choose to encode it into long-term memory, it would quickly overflow. If we were able to just keep information in our short-term memory for a long time and it all built up and built up and built up, eventually you would be overwhelmed with information. So it is, again, kind of adaptive that we can only store so much information for a short period of time. But if we really want to remember that information, we are able to kind of work on it in some way and encode it into our long-term memory. So this is just kind of an example of how chunking might be an efficient way to remember certain information. In this example, it's talking about basically interviewing chess experts. And what they did is they basically took people who were experts at playing chess, and they took people who were just random players, so people who weren't, particularly skilled at chess. And if they had a random display of pieces that were kind of all over the board, we saw very little difference in between the non-experts and the experts and how many pieces they could recall. So if they were asked to recall where all of the pieces were on that chessboard, both the experts and non-experts couldn't really recall much different in terms of the amounts of pieces. However, if you structured the pieces, so say for example in that first display, you have an opportunity where there would be a white checkmate in 4 moves, and that's probably a common display that chess players would have seen many times, especially if they are experts and they played many, many games of chess. So in that case, we saw that the expert chess players could recall far more pieces and their locations than the non-expert players. And that's because instead of viewing them as all individual pieces, the expert chess players were able to chunk basically that display of pieces into meaningful units, because to them that structure meant something specific in that context. So they didn't have to recall every single individual piece. they could recall kind of the general structure, and that helped them in their recall when they were asked to tell you where the pieces were. So we could definitely see how chunking, based on something you're familiar with, in this case the expert chess players being familiar with that particular kind of structure on the board, that can help them recall significantly more information. Now we'll talk a bit about long-term memory. So long-term memory is our final store in the Atkinson-Shiffrin model, and it's a memory store that holds information for extended periods of time, if not permanently. Its capacity seems to have no practical limits. So it's important to note that when we're talking about long-term memory, there doesn't seem to be any particular duration or any particular capacity for long-term memory. Theoretically, we could hold an unlimited amount of information in our memory forever. However, once the information enters into long-term memory, because it is so enduring and we keep things there for years and years and years, the information has to be organized in some way. Otherwise, it would just be a jumble and we would never be able to recall anything. So one way that our brains organize information is to sort things into what we call semantic categories. So participants in memory research often recall items in semantically related groups. So for example, if I read you that list of words from the DRM procedure that I read at the beginning of this lecture, you could see that all of them were kind of related to food, bread, sandwich, all that kind of thing. So if I read you a list like that, and then I read you another list of, say, tools that are used commonly by carpenters, you'd be more likely, when asked to recall all those words, even if I had kind of said them in a random order, you'd be more likely to kind of recall them in groups based on their meaning. So you'd probably be more likely to recall the food words together and more likely to recall the tool words together in a group. So this research suggests to us that semantically related items are stored near each other within our long-term memory. So basically what happens is if you recall the concept of bread, that concept is probably stored pretty near to the concept of sandwich and the concept of crust and the concept of jam and things like that. So therefore, it's easier for you to recall that information at the same time because we hypothesize that they are stored next to each other in your memory. Long-term memory is also organized based on the sounds of the words and how they look. So this helps to explain something called the tip of the tongue phenomenon, when you are able to retrieve similar sounding words or words that start with the same letter but can't quite retrieve the word you actually want. So for example, if you were trying to recall my name, Sally, you might say, like Sarah, Susie, words that kind of sound similar. They have like a similar sound or length to them. Sorry, now I have phones ringing in the middle of my lecture as well. But I'm almost done the slide, so I really don't want to restart recording it. So basically, yeah, that was an example of the tip of the tongue phenomenon. So when a word sounds similar or kind of looks similar to another word, we're more likely to kind of recall them when we're searching for a specific word, which again indicates that those concepts are probably stored fairly close together within our memory storage. So here's an example of the tip of the tongue phenomenon, which is really hard to say. It's kind of like a tongue twister in itself. So if somebody were to ask you, who is this man? So maybe you start thinking of, I know his face, I know he's from Vancouver, I know he's tall, I know he was an actor who was in Deadpool. If you start recalling that type of information, then that means looking at him has activated your semantic network. So it's basically activated a whole bunch of things that have a similar meaning or are related in meaning to who he is. So maybe by remembering those things, yeah, he was an actor, this is where he's from, this is what he looks like, that might help you recall his name. Another way that you might recall his name is thinking, oh, I know it starts with R, is it Ryan, is it, other names, and then when you think Ryan something, is it Ryan Gosling, Ryan R? So you're thinking of words in that case that kind of sound like the word you're looking for, sound like his name. So that would be kind of related to that tip of the tongue phenomenon, where you're basically kind of coming up with words that sound similar to the word that you're looking for. So if you're able to integrate this information, both the sound, the phonological information, and the semantic information, then hopefully that will help you access the memory of the actual name. So if you're able to integrate that information successfully, then you will recall the proper name, whereas if you have unsuccessful integration, you might be stuck with that tip of the tongue phenomenon, where you're saying, you know what, I know it starts with R, I know it sounds like this, I just can't think of what it is. and you might just come up with a bunch of words that sound similar to it. So in real life, we're often required to use both short-term memory and long-term memory at the same time. The distinction between short-term and long-term memory can be observed in a simple experiment. So if I were to ask you to study a list of 15 words and try to recall them all, the results of those types of studies, which have been done over and over again, can be illustrated by what we call a serial position curve. So there's something called the serial position effect, which shows us that in general, most people recall the first few words and the last few words from a list, but only a word or two or an item or two from the middle of the list. So the first few items seem to be remembered due to something called the primacy effect, because they have begun, by the end of you reading that list, they've begun entering your long-term memory. So they've begun the process of encoding. Whereas the last few items tend to be remembered better than the middle of the list because of something called the recency effect. And that is hypothesized to happen because they are still within our short-term memory. So the last few things we heard, they're probably still stored within that short-term memory, so we're able to access them really well. And the first few items on the list, by the time we get to the end of the list, we've hopefully started kind of encoding them and maybe even committing them into our long-term memory. But the ones in the middle of the list seem to kind of get left out. So this is a graph that kind of shows what a typical serial position effect will look like. So if you look at the percentage correct of the words in the list, you'll see that the ones in, first, second, third position tend to be remembered fairly well, which illustrates that primacy effect. And then the ones in the 13, 14, 15 position tend to be remembered really well, which illustrates that recency effect. Whereas the words in the middle, unfortunately, kind of get lost. So the next thing we want to talk about is related to that serial position curve that we just saw. So we're still considering how to distinguish short-term memory from long-term memory stores. So the shape that we observed in that curve suggests that there are two different processes at work, but how do we explain the dip in the middle? So obviously we said that probably we remember the first things on the list because of the conversion into long-term memory, and we remember the things on the end of the list because at that point they're still in our short-term memory, but how do we explain why we tend to forget the things in the middle? So memory researchers blame two different mechanisms. The first is that the items at the beginning of the list produce something called proactive interference, which is a process in which the first information learned occupies memory, leaving fewer resources left to remember the new information. So an example of this might be, for example, if you were trying to learn a language. Say you learned how to speak French in high school, and then in university you're trying to learn how to speak Spanish. So basically, if you are talking to someone after your Spanish course in university or in college, and every time you try to come up with a Spanish word, you end up saying the French equivalent instead, that would be an example of proactive interference. So something that you learned first is interfering with your ability to remember information that was learned later. The last few items on the list create something called retroactive interference, which is basically the opposite of that. So the most recently learned information overshadows some older memories that have not yet made it into long-term memory. So an example of this might be, say if you were at a party and you were learning the names of a bunch of people. So maybe you met a girl named Karen, you met a girl named Susie, and then you met a girl named Samantha. And so if you then kind of encounter Susie or Karen later in the night and you mistakenly call them Samantha, that would be an example of retroactive interference. So the most recently learned information, which was the name of the newest person you met, is interfering with your ability to remember the older information. So we have a little diagram here that kind of portrays the difference between proactive and retroactive interference. So if Sam was asked to remember a list of 10 words, as we know from the serial position effect, he's probably more likely to remember the first word, so happy, train, carrot, and water, and recall the last word, so candy, hike, and telephone. However, the words in the middle, bus, sky, and cat, are the ones that he's most likely to miss when he's recalling the words. So the way that the retroactive and proactive interference would affect this scenario is that after hearing those first 4 words on the list, the proactive interference might make it difficult to remember any additional information. So those first words are going to interfere with his ability to remember the subsequent words. And kind of conversely to that, after hearing the last 3 words, The retroactive interference makes it difficult to remember the preceding words. So basically both types of interference are coming into effect here, and the result is that they're both acting to make those middle words less likely to be remembered. So as a result, Sam could not recall the words in the middle of the list. So neuroimaging has also shown support for different mechanisms underlying the primacy, which would be more related to the hippocampus, and the recency, which would be more related to the sensory areas of the brain, effects. So basically what we see is that it seems like these effects are coming from different areas within our brain. We have also seen that it is possible to separately affect the primacy and recency effects. So if we present things faster, if we basically say the words really quickly, it seems that that leads to a reduction in the primacy effect. So again, if we're thinking that the primacy effect is due to the fact that you've committed those initial words to long-term memory, the faster you present those words, the less likely that people are to be able to kind of get those words into their long-term memory before moving on. And so that would kind of make sense there as well. So the relevancy of kind of distinguishing between these two effects and distinguishing between short-term and long-term memory is basically that the fact that it is possible to separate short-term and long-term memory suggests that simple tests can be used to predict where brain damage has occurred. So for example, if we see that in the primacy effect, which we're talking about being more related to long-term memory, we have the hippocampus active, and the recency effect, we see the more sensory areas of the brain active, then if we see that they're having difficulty with long-term or short-term memory, we can that can help us to estimate what area of the brain the damage might be in. So the Atkinson-Shiffrin model, this 3-box model of memory, provides a great introduction to the different stages of memory formation, but memory is much more complex than can be illustrated in a box and arrow diagram. So in order to kind of fully understand all the nuances of human memory, we must move beyond this model to examine more complex aspects of human memory. So that leads us to our next topic, which is the working memory model. So say you're driving down the highway and the radio DJ announces a contest to win an all-expenses-paid trip to Costa Rica. What do? Obviously, you want to call the radio station, but you're in the middle of a highway. You're driving, so you have to pay attention to your driving, but you're also going to want to remember the number that the DJ told you so that you can call once you kind of pull off and have a safe space to do so. So you're probably going to attempt to remember the number he gave using rehearsal, which is basically repeating the information until you do not need to remember it anymore. But you also need to focus on driving at the same time. So the complexity of this type of task requires a slightly more complex model of memory than has been previously discussed. So a researcher named Alan Baddeley suggested a theory of working memory. So essentially, working memory is defined as a model of short-term remembering that includes a combination of memory components that can temporarily store small amounts of information for a short time. So if you are high in working memory, it has been correlated with things such as high scores on intelligence tests and on tasks which require more complex cognitive function and a control of attention. And those who do well on working memory tasks also tend to stay on task longer during challenging activities. So the working memory model, and we'll discuss the different components in a minute, recognize that stimuli are encoded simultaneously in a number of different ways. So it's not just stored as a single unit. Therefore, our working memory can be subdivided into 3 different storage components. We have something called the phonological loop, which deals with sound information. We have the visuospatial sketchpad, which deals with visual and spatial information, and the episodic buffer, which helps to kind of combine the two. So the phonological loop is a storage component of working memory that relies on rehearsal. So it stores information as either sounds or in an auditory code. So again, if you were in that scenario we just described a minute ago where you're driving down the highway and the DJ tells you the number to call, the phonological loop is going to be responsible for keeping that number in your head. You're going to kind of repeat it over and over until it's safe for you to pull over and call. So this feature of working memory is subject to what we call the word length effect. We can remember more 1-syllable words than 4- or 5-syllable words. So it kind of makes sense. If you're trying to remember a sentence, it's going to be a lot easier if you have a lot of smaller words that are, 1 or 2 syllables rather than multi-syllable words. You're going to be able to obviously store more information the less syllables a word has. It appears as though working memory can store as many syllables as can be rehearsed in 2 seconds. So it differs from chunking. We talked about chunking and about short-term memory storage, but both can be correct in different cases. So the amount of memory that can be stored in your phonological loop as an auditory code is in addition to the 7 plus or minus 2 digits that you can keep in your short-term memory. Next, we have the visuospatial sketchpad, which is a storage component of working memory that maintains visual images and spatial layouts in a visuospatial code. So in that example we were talking about before, you would not only have to use the phonological loop to keep the number in your memory, you would also have to navigate your scenario. So you're in the middle of a highway, there are cars everywhere. You need to be able to have information stored about where the other cars are relative to you, and how it's going to be, you're going to create a safe path for you to kind of get to the side of the road so you can stop and call. So the visuospatial sketchpad engages portions of the brain related to the perception of vision and space, but it does not affect the memory for sounds. So again, this is kind of in addition to that phonological loop which stores the auditory information. So the items stored can be counted based on visual features such as shape, color, and texture, and the information stored in the visuospatial sketchpad may use a form of chunking known as feature binding. So for example, obviously if we think of the features of something, so if you are looking at a car as you're driving down that highway, you might see it's red, you might see it's shiny, you might see 4 wheels. There are a bunch of different features that you can attend to, but you wouldn't store them all separately as different things within your visuospatial sketchpad. You would store them as a single unit. So you would say, this is a car. So you're able to kind of chunk or kind of bind the features together, combine the visual features into a single unit. So instead of remembering all the individual features, you remember what the overall unit was. So after feature binding, visuospatial memory can accurately retain approximately 4 whole objects, regardless of how many individual features they have. So again, if you bind red, shiny, smooth wheels into car, then that would consist of one of the 4 objects that you can store within your visuospatial sketchpad. And then finally, with respect to the storage components of working memory, we have something known as the episodic buffer. So the episodic buffer is a storage component of working memory that combines images and sounds from the other 2 components into coherent story-like episodes. So for example, we're taking the number that we heard, we're taking kind of the visuospatial information we're using to navigate our environment, and we're putting that together to think, I was driving when I heard the DJ give a number to call. So it kind of combines the elements from those other 2 storage areas to help create kind of a coherent story. The buffer is the most recently hypothesized working memory system, and it seems to hold about 7 to 10 pieces of information. These can actually be combined with other memory stores. So the buffer basically means that you can remember 7 to 10 more words when reading meaningful prose than when reading a list of unrelated words. So basically all that's saying is that if you're able to assign meaning or kind of put things together in a meaningful way, it helps you remember more information, which kind of makes sense and will relate to some of the types of memory and encoding that we'll talk about a bit later in the chapter. So again, obviously, as humans, we can remember a sentence that's more than 7 words long, 7 or 9 words long, and that's because if the words in the sentence are kind of strung together in a meaningful way, we are able to store that whole memory. We're not just listening to 7 words and then forgetting what we're talking about, because if we're able to relate them to each other, we can remember even more. So it appears as though working memory is able to connect the prose with information found in the long-term memory in order to help increase our memory capacity. And then last but not least, with respect to our working memory model, we have something called the central executive. So the central executive is the control center of working memory. This is the only component of working memory that's not actually used primarily for storage. So it coordinates attention and the exchange of information among those 3 storage components. So we have our phonological loop, which stores the sound info. We have our visuospatial sketchpad, which stores the visual and spatial info. We have the episodic buffer that helps combine the 2 and kind of add meaning. And then the central executive is basically just, it does exactly what an executive does. It kind of controls the other components. So the central executive examines what information is relevant to the person's goals, interests, and prior knowledge, and then focuses on the component whose information will be the most useful in that situation. So basically it's the one that would say, remember the number, now watch the traffic, now remember the number, now pull over, now call that number. So it seems that regions in the frontal lobe are responsible for carrying out the tasks of the central executive, which makes sense because the frontal lobe and especially the prefrontal cortex are the most recently developed parts of our brain. So they're the ones that tend to be involved in most logic and kind of reasoning skills. And we'll talk about that a lot more in the biological psychology chapter. So here's a little kind of example and a figure of how those pieces might all work together. So you have your phonological loop in this scenario that's repeating to itself the number over and over and over. You've got the visual spatial sketch pad, which is helping you understand the flow of traffic and where other cars are relative to you. You have the episodic buffer, which is understanding the context and blending the information, so kind of telling you, okay, based on this information I'm remembering, I need to use this to help me pass a car so I can pull over and find my phone to call the number. And the central executive is kind of like the boss who's saying, watch traffic, now listen, now watch traffic, now call that number. So it's kind of controlling all the other components. It doesn't actually store any information itself. It just helps control the other components of working memory. I know that this stuff is pretty complicated with the working memory. It is something that honestly, even up until a couple of years ago, we didn't even talk about the different components of working memory in this course. So I understand it might be a little confusing, but as long as you can remember kind of the basics of each component and kind of that the central executive is the one that kind of pulls everything together and kind of controls the others, that should be pretty much all you need to know for the context of this course. I won't ask you a short answer question about it. If anything, I would ask you some multiple choice questions on the different components. So I wouldn't worry too much about it because I know it is kind of a complicated topic. So now we're going to talk a bit about the contents of long-term memory. So up until now, we talked about the Atkinson-Shiffrin model, the 3 different types of memory. We talked about working memory and how that can kind of work in addition to those 3 storage components. Now we're going to talk about how do we actually store the information in our long-term memory. So obviously there are different types of memories. We can have declarative memories, which are memories that we are consciously aware of and that can be verbalized. So 2 major types of declarative memories are talking about facts about the world, so things you might have learned in school. Ottawa is the capital of Canada. There are, 10 provinces, 3 territories in Canada, things like that. That will be our declarative memories. So that's one type of declarative memory. The other type is memories about one's own personal experiences. So the key here with declarative memories, also known as explicit memories, are that they are things that we can talk about. They're things that we can declare that we know. On the opposite side, we have something called a non-declarative or an implicit memory. So these are actions or behaviors that we can remember and perform, but they don't necessarily involve conscious awareness. So they're about things that we can't really declare or kind of tell you about. So for example, if you learned to ride a bike as a kid, you probably still know how to ride a bike. If I gave you a bike and you got on that bike and started riding, you'd probably do a great job. And you might not necessarily be able to tell me exactly how you know it. You might not necessarily remember when you learned it, but you are able to do it. So in that way, it's a non-declarative memory. You can remember it and perform it, but you might not necessarily be able to explain how you learned it or how you know what you know. So there are 2 types of declarative memories, and I kind of mentioned these a minute ago. You have your semantic memories, which are the ones I was talking about that include facts about the world, so how many provinces, the capitals, maybe what a word is in a different language. And then you also have episodic memories, which are memories of your personal experiences that seem to be organized around kind of like episodes. So they're recalled from a first-person perspective. So whenever you recall a memory of, say, your 7th birthday party, or your wedding day, or the birth of a child, or your graduation day, those would be considered episodic memories. And the way that I kind of think of them is that if you were to watch a TV show, that's the kind of things that you watch on an episode of a TV show, right? Events that happen in someone's life. So your semantic memories are kind of facts and things that you know, things that you have learned, knowledge that you've acquired. And your episodic memories are your personal experiences. Often both of these representations are active at the same time. So obviously if you learn something semantically, maybe you might remember the exact scenario in which you learn the names of the provinces in Canada. So in that case, the names of the provinces will be the semantic part, but the episodic memory would be the situation in which you learn that information. So often both of these are kind of activated at the same time in that way. Unfortunately, we do tend to see that episodic memories decline more rapidly as people age. So people tend to hold on to the facts that they've learned, but their personal memories about things that have happened to them and their families, those are the ones that unfortunately tend to decline a little bit more as people age. So then we have our non-declarative memories, which also fall into one of two subtypes. You can have procedural memories, which are basically defined as a learned pattern of muscle movements. So it's kind of like your motor memory. So again, when I talked about, knowing how to ride a bike, knowing how to hammer a nail, knowing how to braid your hair, those are procedural memories, right? Those are learned patterns of muscle movements. You might not be able to explain exactly when you learn them or how, but you're still able to operate and perform those procedures. And then the other type of non-declarative memory is your classical conditioning, or your conditioning memories. So if a previously neutral stimulus produces a new response due to association with an unconditioned stimulus. And don't worry too much about those words for now. When we get into the next chapter on learning, we're going to talk really in depth about all those different terms. But for now, just consider it to be kind of something that you've learned through experience, that you may not necessarily even remember learning, but you have kind of an automatic association. So your textbook gives the example of an amnesiac woman, so somebody who has amnesia. She can't really remember things for a period of time. And basically at one point, there was a researcher who had shaken her hand and he had a pin in his hand, and so he pricked her with the pin. And from that day on, whenever she encountered him, she refused to shake his hand. She couldn't say why. She didn't remember that he had stuck her with the pin, but based on her muscle memory and her body, there was kind of an automatic association there that, hey, I shouldn't shake his hand for whatever reason. So even though she couldn't declare it, she couldn't talk about it, she still had that memory, that kind of conditioned memory that affected her behavior. And the last little part we're going to talk about in this chapter, and I don't want to spend a ton of time on it because, again, we have a whole biological psychology chapter where we'll talk about this stuff in depth, but we will talk very briefly about the cognitive neuroscience of memory. So whenever we're talking about neuroscience, we're talking about basically brain areas and how they affect our functioning. So there was a Canadian neuroscientist, named Donald Hebb, and he proposed that cells that fire together wire together. So basically all that means is that if you have an association where two types of cells in your brain are being activated at once, they become associated and then they tend to kind of fire at the same time during later encounters. So basically he said that long-term memory involved lasting structural changes in the brain. So this is due to a phenomenon called long-term potentiation, which demonstrates that there is an enduring increase in connectivity and transmission of neural signals between nerve cells that fire together. So for example, and this is kind of another thing that talks about conditioning, which we just mentioned in the previous slide, there's something called eye blink conditioning, where basically you might make a certain sound, maybe you press a tone on a keyboard, and then you blow a puff of air into a participant's eye. And so every time you're about to blow the puff, you play the tone. And of course, blowing a puff of air into someone's eye makes them blink automatically. It's not a conscious response. It's not something they try to do. But basically what will happen is that if every time before you make that sound, after you make that sound, you blow the puff of air in their eye, eventually they will start to associate that sound with the puff of air, to the point that through classical conditioning, you can make the sound and they will automatically blink. You don't even have to blow the puff of air anymore. So basically what that's referring to in this case is that because every time you blew the sound, or you made the sound and that activated those neural pathways, then you blew the puff of air and that activated the neural pathways to make you blink, those connections in your brain start to kind of wire together. So eventually when you activate one by making the sound, it automatically activates the other by making you blink. So you can see how over time, if those two responses become so associated, then it can actually change your neural circuitry and make it so those two brain areas are being kind of automatically activated at the same time. So many researchers believe that this long-term potentiation underlies the majority of types of learning and memory formation. However, the relationship between neurons firing at the same time is not permanent. Obviously, if they fire together, they're going to become more likely to be associated, but long-term memories can remain vulnerable to disruption for some time after they are stored. So in that case, we need to perform what's known as consolidation. So memories become more permanent or solid through a process known as consolidation, which basically converts the short-term memories into long-term memories in the brain. So, of course, that long-term potentiation is part of that, but it's not everything you need to kind of make sure that consolidation occurs. For example, consolidation is often aided, at least we believe so based on what we've seen, by sleep. So a lot of the time, if you learn something right before you go to sleep, you're more likely to kind of remember that because, again, this is hypothesized, but maybe those pathways keep activating while you're sleeping and kind of strengthen that connection. So when neurons fire together a number of times, they basically adapt and they make the changes caused by long-term potentiation more permanent, which is known as cellular consolidation. So now we're going to talk just briefly about amnesia. Obviously, we know that our memories provide us with competence and they give us a sense of our personal identity. If you weren't able to remember any of the experiences you've had or things that have happened to you, you'd have a very hard time having a sense of who you are as a person. So how would you feel if you were never able to form any new memories? This is basically what happens to people with dementia or with certain types of brain injuries or disease. So Henry Molaison, who's more commonly known as HM, you'll hear about him in almost any psych course you'll take, is one of the most intensely studied and well-known cases of the loss of capacity for memory formation. So he was no longer able to transfer memory from short-term into long-term memory. So basically what happened to him is that he was 27 and his hippocampus, most of his amygdala, and a portion of his temporal lobes, which are the lobes that are kind of located right behind your ears, were removed in a last-ditch effort to rid him of debilitating and life-threatening epilepsy. What was found was that his seizures did decrease, but his memory was unfortunately profoundly affected. He was unable to recall the day of the week, what he had eaten for breakfast, or even what year it was, and he was unable to remember new experiences for any longer than 15 minutes. So you could go into his room and introduce yourself, and then if you came back 20 minutes later, he wouldn't even know who you were. So he suffered from what we call amnesia, which is a profound loss of at least one form of memory. Interestingly, he was able to retain memories of his childhood and of the nurses who treated him before the surgery, but he was unable to learn any new names. So it didn't seem like the problem was with the retrieval of long-term memories. It was more that he couldn't create any new long-term memories, which is really interesting. So just to kind of call back to our last chapter on research methods, what kind of research is this an example of? I'll give you a second to think of it, but you should see pretty clearly that this would be an example of case study research, right? Because it was only one person, we're studying him intensely because he was the one who had this surgery and undergone these kind of major effects to his memory. So even though we can't definitely generalize and say this would absolutely occur with everyone else, it really gave us some interesting ideas to consider as to what brain areas are important to what types of memory. Because we saw that certain brain areas were removed, and then we saw that certain types of memory were affected. So his problem seemed to be with the encoding of new information, which is a specific type of amnesia called anterograde amnesia, which refers to the inability to form new memories for events occurring after a brain injury. So there are two types of major amnesia. Anterograde is when you cannot make any new memories, and retrograde, which we'll talk about in a minute, is when you can't recall things from preceding the injury or the surgery. So it seemed that his deficit was not due to issues with his sensory memory or short-term memory, because as we know, he was able to meet people and be introduced to them, and he could remember them for a few minutes. But specifically, he could not transfer his declarative memories from short-term to long-term. So his case taught neuroscientists much about the biology of memory, particularly regarding the role of the hippocampus in consolidation. So as we mentioned before, in order for memories to really be kind of consolidated or like kind of placed into long-term memory, they must undergo consolidation. And then in this case, we know that HM's hippocampus was removed. So the fact that he could no longer consolidate memories was kind of linked at that point to the fact his hippocampus was removed. So that told us that the hippocampus was probably a pretty important brain area with respect to being able to consolidate memories. So you can see, and we've seen this before in other animals as well, that when the hippocampus is damaged, the injury interferes with the consolidation process, but it does not prevent recall of pre-existing memories. So if the lesion to the hippocampus occurred before you tried to teach someone something, then they would fail to consolidate, and then if you tested them on that information, they would fail the test. But if the learning trials, or in this case when we talked about the fact that he remembered the nurses and experiences from before the surgery happened, and he was able to perform consolidation before lesions of the hippocampus, then that would show us that the test was successful. So we'd be able to actually complete, learning tests on that information. And because he consolidated it before the damage, he would be able to pass those tests. So storage, as we mentioned before, is the time and manner in which information is retained between encoding and retrieval. It is an active process. So when we are reminded of stored events or information from years ago, our memories can actually be strengthened. So the more we think about an old memory over time, the more that it kind of becomes strengthened and more vivid in our memory. So this is due to a process called reconsolidation. So even if it's already been consolidated into long-term memory, if we think about it a lot or talk about it a lot, it can undergo reconsolidation and kind of become even more of a strong memory, of a vivid memory within our long-term memory. It's interesting to note that long-term declarative memories are distributed throughout the cortexes of the brain, which is known as cross-cortical storage. So we actually see that even though the hippocampus is very important in consolidating the memories and helping them kind of get to that point of storage, the place we actually store the information in our brain tends to correspond to the type of information stored. So for example, visual memories tend to be stored near our visual cortex in our occipital lobe. Auditory memories tend to be stored near our auditory cortex and our temporal lobes. So we do see that there's differences in where the memories are stored based on the type of information. Recently formed memories have not had a lot of time to develop this cross-cortical network, and therefore they're much more likely to be lost following an injury. So again, I mentioned this earlier, but retrograde amnesia is a condition in which memory for events preceding the trauma or injury are lost. And typically, like this would imply, it's the memories that occurred kind of most recently before the injury. So you're not likely to forget everything about, how to talk, how to walk. You're more likely to forget more of the recent events because they haven't had as much time to become fully consolidated. So here's a little diagram. I think this is the last slide. I'm sorry, I know I went a bit over 50 minutes, but like I said, you can watch a bit of this on Friday if you want for that class, because I'm sure that the next modules won't be as long. But if you look at the difference between retrograde and anterograde amnesia, you can see that amnesia is basically talking about memory problems in general. The retrograde would be the inability to remember what was already known before the amnesia occurred, before the injury occurred. And the anterograde amnesia, which is what happened in HM's case, was the inability or limited ability to form new memories after the onset of amnesia. So definitely kind of a difference between the two types of amnesia there. That is it for Module 1. I'm sorry it was a bit longer than anticipated. We're just under an hour, so if you take 10 minutes, if you want to watch the last 10 minutes of this lecture for Friday's class, that's great. It won't be 40 minutes for the next module, so you'll have more than enough time to finish that and the next module for Friday. But for now, I'm going to end this here and go ahead and record those next modules for you. So I will talk to you in the next video.